everybody. Thank you for coming. Today I'll be talking about Chronon, which is an open source feature and embedding pipeline that's been used a lot for real-time search systems. So a bit about me. I spent a little over 8 years at Airbnb building data infrastructure for machine learning. At the time that I joined, there was no machine learning infrastructure team. There was just a data infrastructure team that would support various product teams across the company. And during that time is kind of when we saw that the data infrastructure for machine learning was a pretty big pain point for a lot of teams. And that's kind of where the initial idea behind Chronon came from. So Chronon was an open source project that we built while at Airbnb. And more recently, about 2 years ago, a couple of us left Airbnb and started a company around the project. That company is called Zipline. You can't see the URLs too well here on these slides, but it's chronon.ai and zipline.ai are the two websites if you want to learn more about the project and the company. So first, a bit of background. As I mentioned, we were working at Airbnb, and we were on this data infrastructure team that was supporting various other product teams in the company. And one of the first use cases that we were working with was a payments team, actually. So it wasn't search yet. We started working with payments trust. And when you think of Airbnb, it's obviously a travel company, but in a lot of ways, it's a traditional payments company where it takes payments from guests, pays out hosts across bank accounts, across borders at large volumes. And as a result, it has a lot of the fraud problems that more traditional payments companies face. So this team was struggling with all kinds of fraud vectors and payments fraud vectors that was costing the company a lot of money. And the main thing that they came to us with was a need to be able to iterate faster. Getting new features into production, especially streaming features and real-time features to respond to changing fraud signals, was a slow and a long process that took a lot of engineering work and a lot of iteration. And they wanted to move faster. So we took a look, and I'll get deeper into what the exact pain points and the frictions there were, but we basically helped them kind of speed up that workflow to train a new model, launch a new feature to production from a couple of months to a couple of days. And so that was a big success, and then word kind of started spreading that, like, hey, there's a better way to do feature engineering for these real-time systems. And so the footprint within the company of this project, it wasn't called Chronon yet, but it was basically the thing that would become Chronon, started spreading. So other trust vectors, like account takeover, came next, and then came search. So search was the second biggest one after the kind of trust and safety and payments use cases. So search, obviously, as a lot of you here probably know, is a level above kind of other ML use cases in terms of scale, latency requirements, sort of just the overall P99 sort of uptime requirements and stability. And so that was kind of another big journey for us internally at Airbnb of improving the engine to be able to work at search scale. But the cool thing was once search was kind of on board and we had a similar impact with them where now they could iterate faster, detect, as kind of the user behavior started changing, they were able to incorporate those changing user activities into the search models better, iterate faster, ship better personalization loops more quickly. Once that worked at search scale, it basically worked for every use case in the company. So customer support came next with issue prediction and chatbot context retrieval. As well as other non-ML use cases. So when you go to Airbnb and you see kind of something like this on the UI, like the average rating there and the number of reviews, that's also being computed by Chronon because that team that produces that and exposes that to users, they want those aggregations to be real time and they want them to be served scalably with low latency in the front end. So it ends up being a very similar engineering problem to the actual ML feature serving. So it was kind of taking off within the company as of like 3 years ago. There was like 30,000 different features being served on Chronon at Airbnb, like tens of thousands of streaming pipelines. And it was going quite well. And so we started thinking about basically open source at that time. And that's when we started talking to the team at Stripe. So Stripe, if you don't know, it's like any kind of payment UI like this across the internet. Is often powered by Stripe on the back end for payment processing. And at the time, the team there was dealing with the same problems that the Airbnb machine learning team was dealing with for payment fraud prediction. So specifically around iteration speed, ability to use real-time features, and so on. So we started talking to them at this time, and we basically decided to do a closed open source with them. So before we basically went fully open source, we kind of partnered with Stripe. We integrated Chronon into their stack across company lines, and we kind of joined the project across the two companies. And as of a couple of years ago, like 100% of Stripe's charge path models, so all the models that do issue prediction from UIs like this across the internet were running on Chronon. So 100% of this traffic is being driven by Chronon. So after that, we went fully open source in 2025, and OpenAI became the next big adopter of the project. So Sora 2 personalization is driven by Chronon now, as well as you can see here, these user-facing metrics here. Similar use case to Airbnb's user-facing metrics, those are also computed in real time using the Chronon engine. Netflix as well has adopted the project for personalization and content recommendation, and many more since then. So that's a bit about kind of the origins of the project and kind of what brings us here. So in terms of scope, what is it? So I mentioned it's a feature and embedding platform. And what that means is that it takes raw data sources from anywhere basically in your company, batch sources, streaming sources, CDC, external API calls. And it's an engine that transforms that raw data into useful features and embeddings and can power both model inference and model training with guaranteed consistency between the two. So, as I kind of mentioned, the use cases that we built this for were things like payments fraud, search ranking, pricing, risk decisioning, as well as some agentic workflows. And so the infrastructure requirements here are pretty stringent, and specifically around, you need low latency, especially for search use cases with high fan out. You need to maintain low latency type budgets. Sub-second streaming freshness. This is really important both for some personalization as well as fraud detection use cases, where as events are occurring, you need those to be reflected in feature values powering prediction with high freshness. Point-in-time correct backfills. This is a pretty big one. So as you backfill data for model training, it needs to be done so consistently, and specifically with temporal consistency to what's being served online. For inference, and as I mentioned already as well, frequent iteration. So you need to be able to let data scientists iterate quickly, add new features, make changes to features, and do this with a relatively easy loop. Beyond that, search, again, search is always kind of the use case in most companies that brings the most interesting sort of requirements as well. And I'm going to talk a bit more about these sort of architectures throughout the rest of the talk. So things like two-tower search involve complex pipelines, chaining features and embeddings, and combining them. Generative recommenders, especially things that use things like semantic IDs as well, have been new architectures that have brought new data infrastructure requirements in the last year or two. And lastly, agentic experimentation is an interesting one that I want to kind of dig into towards the end if we have time. And that's because search is obviously a high-value use case, so anything that we can do to improve the experimentation loop there and get better results tends to drive business value as well. So the rest of this will start to get more technical from here on outwards, and I'll start to go deeper into kind of what are the challenges here and how does Chronon solve them. So first, streaming. So this is I think streaming features is, I think, a classic one that teams struggle with, and it's one that we saw be really difficult, and one of the main motivators for why we decided to kind of tackle it first within Chronon. So for example, right, let's say you have users making purchases, and this can be in some message bus like Kafka or Kinesis or PubSub or whatever, and you want to compute average purchase price by category per user in these various time windows. So what you want to produce is something like this. So for a given user, the 1-day, 30-day, 90-day averages bucketed by these categories. So what does this look like? Or rather, what are the challenges here? So first, you have these long windows, right, like 90-day window, but you also want it to be real-time streaming. So you want to capture both history and recent events. And often recent events are going to be in the message bus, history is going to be in the warehouse, so now you need some sort of Lambda architecture to glue these things together. That in itself is a fairly complex engineering challenge. Low latency with long window sizes. So the naive approaches here involve just storing raw events in memory and aggregating them at read time, but that doesn't scale very well as soon as you get longer window sizes or hotkeys. tail accuracy. So like you can't easily pre-aggregate everything because you also need to say at any given point in time what events are outside of the window on the tail, and you want to be accurate on that as well. And lastly, you need to both serve this online and produce historical backfills for this for model training and keep those two things consistent. So what does this look like in Zipline? Basically, this is the API that we expose to users, to data scientists, for them to define this aggregation. So it's like a few things. I mean, there's a source defined up top where it defines the topic and the table where data comes from. I left that off the screen for here, but basically it's these components, right? So you say, okay, the input to this aggregation is purchase price. We're going to do an average over these windows and bucket by category, right? So that bucket by category is what's going to produce this, basically, this inside thing. You don't need to have a bucket, but in this case, we do have a bucket for this feature. So from there, Zipline automates the infrastructure to serve this online and to do the backfills, basically, and it guarantees consistency between the two. So digging in, what does that infrastructure look like? So as I mentioned, right, it's like the history for this data source is in the warehouse somewhere, and recent events are in the message bus somewhere. And essentially, there's a Lambda architecture that Chronon automates to compute the online feature pipelines for this. And so here's what the batch pipeline looks like. Start by just looking at this this part up here. Basically, what it does is for each of those features, it takes the window, so like that 90-day window, for example, and it produces a single collapsed value for, in this case, 88 days, basically the middle part of that window. And it collapses all that data into one value per key, right? So already we've compressed 90 days of data into, or 88 days worth of data into one key value per key. On the tail, it produces these hops. The size of the hop varies on the size of the window, but it could be basically anywhere between 5 minutes and a day, depending on the size of the window, and this is what gives you the tail accuracy. So these are essentially disaggregated values per time bucket at the tail, and it produces this. The way it produces this is with a Spark job. It's inherently incremental, so it produces these 1 day, like sort of cached intermediate representations. I'll kind of gloss over this a little bit for now, but we'll come back to it later. But basically, that's what this batch job is doing, right? Is producing these two things. And of course, because this is an average and we need to be able to compose these values, it's not just doing the average value. It needs to break the average down into a sum and count pair, which is what the IR is in this case, the intermediate representation of this aggregation. And it needs to do it per bucket, right? So like that bucketing also needs to be part of this IR here. So it does this. And then there's a streaming job as well, right? So this is the second part of the Lambda architecture. So Spark computes this initial tiled state. So this was the batch portion that I showed on the previous slide. And then now there's the Flink job, right? And so the Flink job is going to do a few things. First, it's going to take the raw events in. So this could be, Kafka, Kinesis, PubSub. We actually run Spark eval within the Flink job. This is a detail that we can talk about more at the end if folks are interested. But the nice thing here is it lets you define some transformations on pre-processing in Spark SQL. And you get consistent backfills and batch jobs as well as consistent stream processing in the Flink engine. There's a pretty cool way that we figured out how to do this. But I won't get too deep into it just now. But basically, it converts these raw events to the IR as well. So again, it's going to take that, identify the bucket, some count pair, and then two things happen. So one is that as new events come in, we update the final state per key here. And then also as time moves, right? And so this is one of the nice things about the newer Flink versions. As time moves ahead and events fall out of the tail, we can also do this tail eviction update. So this is how kind of we take new events coming in and keep the values up to date, and we take time moving forward and events falling out of the tail and keep the feature value up to date. And then that final value gets written to the KV store, and that's what's served from the fetcher. So basically what this means at the end of the day, and I know I moved a little bit quickly through this, but we'll have time to come back to this at the end, hopefully, if folks want to go deeper on it. But what that means basically at the end of the day is that you have a single value here that is correct both with real-time updates and with tail eviction updates. And regardless of the window, because we collapse the middle of the window here, it's the same latency and the same payload size for a 1-day window or a 90-day window or a 180-day window or whatever. And all of this is driven from that simple definition that the user wrote, which is just a few lines of Python. And all of this infrastructure is automated. That was a lot. I basically, talked about like sort of half of the zipline compute engine in just 2 slides here. So probably there's a lot of details here that folks might be curious about that I didn't cover. We have actually a lot of writing on this on the Zipline website, a couple of blog posts. But for now, I'll move on. And if there's time at the end, and if folks want to ask more about this, we can talk more about this. But okay, I mentioned backfills before as well, right? So like if you define that feature, like 30, 60, 90-day average with these various buckets, you'll need to backfill that data for model training as well. And so this is the other thing, right? Is like teams often have this issue where we have this feature and we write some Flink job or whatever, and we can kind of produce it and serve it, and it more or less works. But then for model training, you like write some batch SQL, and now you have these 2 pipelines, right? And you kind of hope that they stay in sync and that your Spark SQL logic over here matches your Flink SQL logic up here, and what you're serving online is the same as what you trained on. But it's a very common source of inconsistency and very common source of sort of production issues that teams face. So what we really want with Zipline and with Chronon is one definition to power both backfills and online inference. And so that's why from that same feature definition, you can also essentially generate training data and power these backfills. So that's what we call point-in-time correct backfills. That's this PITC that you see here. So the way that works is there's a spine. So like this is a spine or like observation timeline. Basically, in this case, it would, in most search use cases, it would be things like search events. So that has like primary keys and timestamps, and we want feature values for those. So the way the Zipline, the Chronon batch engine works is it basically takes those spine events in via a query, and then it computes the actual feature values from the raw source data, which is usually in like S3 or GCP or somewhere in the warehouse. But one nice thing that it's able to do, I think I mentioned before that we produce these partial aggregates as part of the batch upload to seed the streaming job with. We're able to reuse these partial aggregates again in the backfill here. So, like let's say in this case we have, let's just consider the 90-day feature, right? So like let's say we're trying to get 1 month of training data and we have a 90-day feature. This 1 month at the head, we're going to read raw events for, and then for the 1 month at the tail, so like, this month minus 90, we're also going to read raw events for because we need to get accuracy on the head and the tail. But everything in the middle, we don't actually need the raw events because those don't fall within the head or the tail of the window. They can simply be aggregated values that are used in the final computation. So that's where we can take essentially the partial aggregate values that were already produced previously elsewhere in the engine for the online upload and pass those into this backfill job, which can then combine these things with these things and produce correct backfill data for your features. So basically, all of this to say, sorry, I had highlights for that, but I was using the laser pointer. So yeah, all of this to basically say that user only has to write this, and what they get guaranteed by the Chronon infrastructure is low latency serving with real-time updates from the streaming job, point-in-time correct backfills, and it's made fast and cheap with this compute reuse concept within the engine. Okay, that was a pretty quick walk through streaming. I want to go through chaining next, and then we'll talk a bit about agentic research. Those are kind of the 3 deep dives, and hopefully I still have time at the end of all that to take more questions. So chaining. This is another very common thing that I think we see a lot in search pipelines, and especially more and more as we do things like semantic IDs or generative recommenders, there's a lot of model chaining involved in these architectures. But here I have a simple one, a very simple one actually. So like take user activities. This could be an event similar to the last one where it's like purchases, but it can include clicks, views, whatever. Enrich the event and collect the last K and transform it into a user embedding. So like here we have like a user ID, item ID, event type kind of event. And what we want to say is like, okay, we have this dim listings sort of table in the warehouse. We want to enrich the category onto this, right? And so now we have this enriched event. And then we're going to do this aggregation to take the last 100 things that a user did and pass that to an embeddings model, for example. So this is tricky, right? This is difficult with a lot of existing data infrastructure. Streaming join is not a simple architecture to build and maintain and be on call for. And it has a lot of the same problems as before, right? So like these problems are the same pain points that we talked about on the last slide. But now you have this multi-stage pipeline orchestration. real-time embeddings generation, there's like a new set of challenges that are coming in here with this chaining use case. So again, our goal here, similar to the streaming aggregation and transformation, is to make the API very simple, expose users to a simple semantic description of what the pipeline is that they want to generate, and then have all the complex infrastructure to power that at scale be automated by Chronon, by the infrastructure. So the way that looks in this case is you'd have this topic, right? So like this is user activities, whatever. This is just some demo stuff that we have set up in our Canary environment. And then on top of that, you do this join. So join is like an API concept here that basically can take a source in as the left side. That was the source that we saw previously. And then in this case, we're basically putting listing features. So in this case, we have listing features that include that category field. That's what we actually care about. And we're saying, hey, take these features and enrich this streaming source with these features, right? So that's like the first part of the pipeline. Now we have this aggregation. This is kind of similar to what I showed you earlier, except for last time we were doing an average. Now we're doing this last case, where we're saying, okay, for each user, take their last 100 categories, which we enriched onto that stream previously. There's a 7-day window in this case, but it could be whatever. And then lastly, we pass it to a model. This is a bit more verbose here, but basically all that this is doing is pointing to an existing model. In this case, it's an off-the-shelf Gemini embedder, but it could be something that you trained yourself and uploaded. This is just an integration, basically, with the model platform. We actually, there's not really a model platform concept within Chronon, but it's an orchestrator that can talk to various pluggable model platforms. There's a bit more, bit more things that I'm not showing here, but at the end of the day, that's the gist of it, right? So that's basically this pipeline expressed in Chronon API. And so, okay, yeah, I have like a little, I don't know how well it's going to show up, but basically, once you write those configs, this is essentially what you get on the other side of that. And this is just the UI visualizing the data flow, basically. I'll do it one more time. Where basically it's like, okay, you have that pub sub event here. User activities, there's a listings pipeline that's doing the listing features, joining those up. And then at the end of the day, it's calling the model transform with the aggregated last 100 of those user activities. So it's nice because it really focuses the API on just the semantics of that pipeline. And then again, all that streaming job, the Flink job, the Spark job, the KV store sort of provisioning, the calls to the model platform from the Flink job to do the model inference, all of that infrastructure is being automated for you. Yeah, and so that's kind of the main concept here, is that you have this way to define these aggregations and these transformations, and that they're inherently composable, so you can build these relatively complex pipelines relatively easily and not have to worry about all the infrastructure under the hood to power it. Okay, agentic experimentation. So this is an interesting thing that's been coming around more. Like we have coding agents, Claude Code, Codex, they're good at writing code. How do we, make them effective at essentially iterating on machine learning models as well, trying out new ideas, setting them loose on that in a way that actually makes sense and delivers value and doesn't cause more problems than they solve. That's the general idea. So the way we kind of have been viewing this and what we've seen work well in this world is basically, agents, they create new features, they can add them to model, they can run model training, evaluate the impact of that feature. And basically deploy end-to-end pipelines all the way to dev. So like if you even want to run an A/B test off of something that the agent did, that should be doable. And everything that the agent does should be production ready, it should be reviewable, and it should be safe. Safe meaning that as you have like more and more agents running things, they're not going to take down production. But basically, where the human comes in is at the end of this to review the changes, make modifications, provide guidances, decide on whether or not we're going to launch an A/B test and send actual traffic to this thing, decide on whether or not we're going to go to production. So far, this is kind of what we've seen be the right setup for this. And so the challenge, again here, the first one is infrastructure. So teams that have used Chronon to do this, to build these kind of agentic loops, these research loops, one of the main values that the Chronon platform provides is that infrastructure automation that I mentioned on the previous slides, right? So think about kind of those same examples that I showed on the previous slides and what the code or what the infrastructure footprint would look like for an agent to try to build those. You would have, you'd have some data on Kafka. You'd probably have like a Flink job, a Spark job. You'd be gluing them together with Airflow. You'd have to think about a serving fleet to do things like, that chaining, like that real-time chaining and model inference calls based on Flink events and things like that. There'd be some observability that it would probably also need to configure on top of that. And basically the result of this is, you'd have an agent making code changes, possibly across different repos, definitely across different languages, spinning up infrastructure. And it can be error prone. The agents like to cheat a lot in this case. That point-in-time correct backfills that I talked about is really nice because it guarantees that when it backfills data with the Chronon API, it's going to get a resulting data set that's consistent temporally and it hasn't leaked data from the future, and it's not going to report some crazy result that you're not going to see in production. But also, it just like it's not reviewable, right? I mean, if you even if you're very familiar with all these technologies and you understand what the agent's doing across the stack, it's still very difficult to review all that code across all those repos and all that infrastructure footprint. And then these last two, it's not necessarily safe or costly. I mean, it's not necessarily safe, and it could be quite costly because this is probably the same infrastructure that's powering, your production workflows. And if you suddenly have a lot of agents, spinning up like jobs and running resources across all of these, then you can quickly be putting load on production systems that's not meant to have supported this sudden increase in experimentation workload. So back to automation, right? I mean, this is sort of the same API that I showed you earlier, right? And so because all the agent needs to do is this, and the infrastructure to power both backfills and serving is automated with consistency guaranteed, it becomes a much more ergonomic sort of API for the agent to work with and to use for iteration. Okay, so we'll get a little deeper now into this concept of safety and efficiency. So essentially what we want to do is something like this at the end of the day. This is obviously a very simplified representation of it, but you have a production model that's being served off like a feature set A, B, and C. And then what you want is like the agent to be able to say, hey, I have an idea for feature D, or a user just be like, hey, try these 10 feature ideas. And for the agent to come along and say, hey, okay, what impact does this actually have on the model? And to be able to author something that could theoretically power an endpoint, right? So like you want the user to be able to say, okay, this thing that you did, we're going to launch an A/B test off of it, and there's an endpoint that actually serves it. Like that's the goal that we want the agent to be able to get to. So the way we do this basically is first resource isolation. So agents will always work on this dev branch, and we have this concept of branch-based resource isolation. So as soon as that agent, every job that the agent runs is run from a branch that is isolated to that agent. And the resources, meaning like the KV store, the Flink resources, the compute resources, all those things are isolated from production. So no matter what that thing does, no matter how crazy this gets, and we'll talk about how to stop it from getting too crazy in a minute, but no matter how crazy that gets, it's not going to interfere with production serving. And it's very nice to have the underlying infrastructure guarantee that for you so that you can sort of sleep easy as you're running research loops overnight or whatever. Okay, and the second thing here is compute reuse. So this is probably what I'll go into more details on next. But we talk about resource isolation, right? Which is good. You don't want the compute of this experiment taking down production. But what you do want is all of these unchanged features to not be recomputed either. And that's where things get kind of interesting. So the way we do this basically is, again, it's provided for you under the hood by the Chronon engine, right? Because like what you wouldn't want is for the agent to try to do this themselves. To be like, okay, there's this data already computed here. I'm going to copy these files over and like take these columns and then like compute these ones and join them in. Because it could probably do that. But if it does that, you're going to have to figure out exactly what it did and then untangle that and then think about what the production pipeline for that going forward needs to look like for, computing new feature values for the upload and for backfills. So, it's doable, but it kind of breaks that goal of having whatever the agent produces should be production ready, right? And so like if it's doing a bunch of random data operations that you need to like then go and audit step by step, it gets quite tricky. So what we do within Chronon actually is just this concept and again, this is another very deep topic that I'm only going to kind of scratch the surface on here. But this concept of semantic hash-based compute reuse. So, the agent's going to produce a diff like this, right? Like, this is like a new feature that it's going to try, something like this, and it's going to run backfill. And that's all it needs to do. And under the hood, what Chronon's going to do in the compute engine itself, when you actually issue that backfill to Chronon, it's going to start with something like this, right? So we have 30 and 60-day features already, and then we have these cached partial aggregates, which we talked about before, which are computed off of raw data. So we have this new feature 7, and it's going to automatically detect, based on the semantics of that feature set that the agent's requesting, that, hey, 7 is the only new one. Everything else is already computed. It's doing this for you. It's going to copy that data from the existing data set over so that these features here are not recomputed. And it's going to compute this one. It's going to use the cached partial aggregate values to compute this one as cheaply as possible if they exist. If they don't exist, it's going to compute it from the raw data. And then it's going to combine these up, and it's going to give you this training set, right? And so the agent doesn't have to try to do this itself, and you don't have to try to audit this behavior that the agent did yourself, right? Which is really nice. It's just handled for you by the engine, by the infrastructure. So the surface area that you need to review and that the agent needs to modify is a lot smaller. And this compute engine is kind of built for the ML use case of basically, it's quite common, right? Adding one feature to a very wide table, and it's like often quite painful. So yeah, basically I'm almost at the end here, but basically this is kind of the foundation that we've seen be useful for agentic experimentation. And I've highlighted the most important things here. Basically, to be able to backfill data cheaply, consistently and efficiently, and to deploy that to production and get those pipelines that, again, can serve scalable, low latency, real-time serving with efficient consistency between the two guaranteed is kind of the most important part. But the foundation, there's a few other things that we've seen be useful here. To the degree that you want to do feature ideation within your platform, we don't have a very strong opinion on this, but there's like a data explorer concept that we've added recently so that things can kind of read the catalog. I think the way you want to wire this up within your stack is very business use case specific. But these two things, I think, if you're doing real-time live systems like search, I think these two pieces of the foundation are really important and some of the nice things that Chronon provides. Yeah, so that is about it. Basically, a single platform for features and embeddings makes streaming easy, makes training easy. Complex pipelines can be built with a simple API. The infrastructure to power them is automated, and consistency is guaranteed between online and offline. Provides a nice foundation for building agentic research loops on top of it. And I think I still have like 6 or 7 minutes or maybe more, something like that. Yeah, thank you.
Thanks, Varant. Plenty of time for questions. Yeah.
Thanks for the talk, really interesting. I saw in your examples, it looked like both your stream joins and your aggregations were either time or event count bounded. Do you support like unbounded operations in streaming or aggregations?
We do. We support unbounded in time, not unbounded in collect set. So like if you're doing a last K, you always have to provide some K. It's up to you. Okay. It's only bounded by big int, maximum integer, but like, yeah, we do force the user to pick something. We don't want it to truly grow infinitely.
Thank you.
Yep. Yeah, unbounded in time actually does make some things easier because you don't have to think about tail eviction anymore. So there are some under the hood optimizations for time unbounded windows. Okay, yeah, for sure. Yeah, I'll be around, yeah.
First thing for the talk, I have a question about the chaining, generally speaking, because since we're talking about streaming, we tend to say that new event, you change the feature and then you need to recompute your embeddings, but it's expensive. Is there any way that we can manage to, I would say, to do not directly each event, but some of events to retrigger the embedding generation?
Yeah. So like kind of more like mini batch kind of thing. Yeah, so I focus a lot on streaming here, and basically real time. Every time a user does something, we're going to update their embedding. Not every use case needs that. Yeah, so that's a good observation, actually. I focus kind of on the very hardest case of the most extreme requirement. There's batch or streaming, basically, schedules. I didn't talk about that much at all. And like a lot of features, even in a real-time system, are coming from a batch source that has like batch updates and, for example, batch embedding updates as well. There's a schedule concept that you can set on every computation. If you provide a topic, it defaults to streaming, and that means like, hey, we're going to do it event-based, basically. But you can do it schedule-based, and there's essentially a cron schedule argument that you can put in the API that says, hey, here's the cadence of which I'm going to update this thing, and the cadence in which I want this pipeline to trigger, basically. So it's like Airflow. I mean, it ends up looking a bit like Airflow if you're familiar with that. And so you can, essentially, user has control over that cadence, basically. Mm-hmm.
Thanks. Other questions? No? So let's thank our speaker. Thank you for the nice talk.
Thank you.